So one of the most important things to realize about alcohols is their acidity. Um, while they are weaker acids than water, uh, nevertheless, they still have a measurable pKa. So under the influence of a strong base like sodium hydride, uh, the proton can be removed from ethanol to give sodium ethoxide and liberate the hydrogen as hydrogen gas. Alkali metals such as sodium, potassium, or lithium are often used to treat alcohols to make the corresponding alk oxide. So we can make sodium ethoxide, potassium ethoxide, or lithium ethoxide from ethanol and the alkali metal. In comparison to halides, which can form a stable conjugate base because they're able to stabilize the negative charge, the alk oxide ion, to a lesser extent, but still fairly well, is able to stabilize that negative charge. Amines are less stable bases because they're or less acidic because their conjugate base is less stable. The charge on the nitrogen can't be stabilized as well. And then a carbon atom is least stable as a negatively charged species. So we're going to use the Areo mnemonic, which was atom, resonance, induction, and orbital, to rationalize the relative acidity of an alcohol. So looking at pKa's, the halogens form strong acids with pKa's ranging between -10 and 3. And HCl, very strong acid, HBr, HF, these are acids with measurable pKa's. Water has a pKa of 14. We can derive that. An alcohol has a pKa of 15 to 18, so not as strong an acid as water, but not far off of that. Looking at an amine, even less strong of an acid, pKa of 35 to 40, and then an alkane, the weakest acid of all in this comparison, pKa of 45 to 50. So using the Areo mnemonic, the atom, the electronegativity of the atom is responsible for being able to stabilize the negative charge, with the halogen being most stable, oxygen being second most stable, nitrogen third most stable, and carbon the fourth most stable. Now, looking at the pKa of cyclohexanol compared to phenol, the pKa of phenol is a smaller number, so a stronger acid. Phenol is a stronger acid than cyclohexanol. But we can't, in the Areo mnemonic, atom, resonance, induction, orbital, we can't use the atom to explain it because in both cases it's an oxygen atom. So we're going to invoke resonance to explain this difference between cyclohexanol and phenol. Phenol is, more than 1 million times more acidic because the phenoxide ion is resonance stabilized. So after ionization, we have the electron pair coming down, and then this double bond electron pair moving onto the carbon to give us our first resonance structure. And this can continue to give us these 5 resonance structures, or 4 resonance structures. This one, the first one and the last one are identical. These 4 resonance structures for phenol. So that explains the relative acidity of phenol compared to cyclohexanol. Now, if we look at the acidity comparison between ethanol and trichloroethanol, again, the atom is the same. We have oxygen. We don't have any resonance structures to draw that would explain a difference between ethanol and trichloroethanol. So induction would be the third order effect to look at. In the case of a trichloroethanol, the chlorine groups, because of their high electron or high electronegativity, withdraw charge density from the carbon, partial negative charge on these chlorines. And that would typically give a partial positive charge on this carbon. And the electron density on this oxygen can be, through the inductive effect, can be spread to this carbon so that the partial positive charge can actually be experienced here, or to some extent here, by allowing the electron density to move to this carbon. Now, salvation effects can also explain difference in the acidity. In an ethanol molecule, when ionized, the number of solvent molecules that can orient around the negative charge to help stabilize that by putting the positive dipole of the solvent in alignment with the negative charge of the oxygen. More solvent molecules can fit around this primary alcohol than in the case of this tertiary alcohol. So our alpha carbon has one carbon bond, so this is a primary alcohol. In this case, our alpha carbon has 3 carbon bonds, so this is a tertiary alcohol. The solvent molecules are sterically hindered from aligning with this, with the negative charge on ionized butanol, so it is less stabilized, which reduces the acidity of T-butanol. This figure shows what I was just speaking about, that the number of solvent molecules that can fit in here. So you have the negative charge on the oxygen, you have the positive end of the solvent dipole aligned with that negative charge to stabilize it. You can fit more of these molecules around the negative charge here than you can in the case of the T-butoxide ion. So stabilization is greater. This is lower energy. It's more. It's going to be better able to ionize because it's going to be better stabilized in that ionized state.